You know, there's this idea in bow hunting, and it's pretty deeply ingrained, I think. You've probably heard it a million
Oh,
times.
yeah.
That if you put that arrow right in the boiler room, right? Perfect shot placement. The rest is just details. Clean kill, done deal.
Mm-hmm. The gold standard.
But what if I told you that years of pretty careful research actually throw some cold water on that? Seriously.
Go on.
We're talking documented cases, loads of them across all sorts of tough stuff like zebra, wildebeest.
Right. Really challenging animals.
Yeah, but also elk, moose-sized animals,
Yeah.
even down to whitetails, nyala, pigs, hunters using decent draw weight bows, making shots that looked, for all the world, perfect.
Textbook shots, you'd think.
Exactly. And yet, non-lethal hits. The animal wasn't recovered quickly or sometimes at all. It kind of makes you stop and think, doesn't it?
It really does. And, for anyone listening who's keen on really getting bow hunting figured out quickly and properly, well, situations like that are a big puzzle. We all focus so hard on hitting that spot. But maybe the question we should be asking is, uh, what about the arrow itself? What role does it play even when the shot looks good?
Exactly. And that's really the mission for this deep dive today. We're going to unpack what Dr. Ed Ashby's 2007 study update, specifically Part 2, found.
A really significant piece of work.
For sure. And this isn't just theory, right? It's built on years of actual field data testing. It goes way beyond just common assumptions.
Real-world results.
And what it shows is, yeah, there are these absolutely critical factors for getting this consistent, clean kills, factors that go beyond just hitting the X. And this stuff, it matters whether you're just starting out or you've been doing this for years.
Absolutely. It's about understanding what truly makes an arrow lethal. And Ashby's work, it just flies in the face of that shot placement is everything idea.
It really does.
The data he gathered, it just clearly shows that the arrow, its characteristics, how it performs on impact, it's just as vital. Maybe even more so sometimes.
Okay, so let's dig into that. The study found this common thread, right? In those shots that looked perfect, but, well, weren't lethal.
Yes, a very distinct pattern emerged.
With basically only one single exception in all those cases they looked at, the problem came down to structural damage somewhere in the arrow system.
Right. Not just a dull broadhead, we're talking.
Yeah, more fundamental stuff,
Yeah.
like the shaft itself cracking or the insert bending or some component just failing.
Exactly. And the critical thing to grasp here is that any kind of structural failure, doesn't matter how small it seems, it just eats up the arrow's energy. It's kinetic energy.
Okay, explain that a bit. Dissipation.
Yeah, think about efficiency. If the arrow shaft flexes too much and breaks, or the insert buckles, the energy goes into braking the arrow, not driving it forward.
Ah.
It's like trying to punch through a board, but your wrist gives way on impact. The force just doesn't get delivered where you need it.
Gotcha. So if shot placement isn't the absolute king, what does Ashby's study say is the #1 requirement for lethality?
It's really unambiguous in this study. Arrow penetration. Getting enough penetration is the first thing you need for a lethal hit.
I sense.
I mean, think about it. You could have the sharpest broadhead ever made, right?
Eh?
But if the arrow doesn't actually reach the vital organs, that sharpness is totally irrelevant.
Yeah, a super sharp knife that just scratches the surface isn't doing the job.
Yeah.
Crystal clear point. So, penetration is primary. What then is the most critical factor for getting that penetration?
Okay, so looking at all the things that affect penetration, the study highlights structural integrity as being #1. Absolutely paramount.
Structural integrity,
Yeah.
above all else.
Yeah, because if that arrow shaft bends excessively or snaps on bone, or if the insert or adapter fails, the energy needed to push through is just lost right there in the failure itself.
Yeah.
A really solid, structurally sound arrow, though, it's going to transfer a much, much higher percentage of its energy into actually driving that broadhead forward through hide, muscle, bone, whatever it needs to get through.
Okay, structural integrity first. What's next on the list? What's the second most important factor, according to the research?
Coming in right behind structural integrity is the quality of your arrow flight. Good, clean arrow flight.
Okay, why a second?
Well, the study puts it after integrity because, look, even a perfectly flying arrow is useless if it just disintegrates on impact, right?
It's true.
But it comes before other factors, because if your arrow isn't flying straight and stable, if it's wobbling or porpoising, it just negates any other advantages you might have built in.
Yeah, that makes perfect sense. Like throwing a wobbly football, it just loses power and accuracy.
Exactly. An arrow flying erratically bleeds off energy in the air, and it's
Yeah.
way less likely to hit straight on and penetrate deeply.
Okay. So integrity first, then flight. Now, where does our accuracy, the archer's skill in hitting the target, fit into all this? You know, the old you can't kill it if you can't hit it line.
And that's obviously true, right? You absolutely have to be able to hit the animal accurately. That's fundamental.
Of course.
That.
Mm-hmm.
The study offers this really interesting counterpoint. It says you could theoretically put an arrow right in the sweet spot. Perfect vital hit.
Uh-huh.
But if that arrow itself lacks the structural integrity or the overall design for penetration,
Hmm.
it still might not result in a quick, clean kill.
Hmm.
So the arrow itself, your whole setup, has to be capable of being lethal when it hits, even if the hit isn't, absolutely textbook perfect every single time.
That's a really crucial distinction. It's not just hitting the animal, it's hitting it with something that can actually do the job effectively once it gets there.
Precisely. And let's be honest, hunting shots are dynamic. Things happen fast.
Yeah, they're rarely like shooting at a bag target.
Exactly. Animals move.
Yeah.
You might be shooting from an awkward position. The angle changes. Ashby even noted in his observations that a lot of the shots he witnessed in the field were, let's say, marginal, less
Right.
than ideal. Truly perfect shots were actually kind of rare. So that leads to this critical question the study implicitly asks. What's the bigger challenge in bow hunting success? Is it just hitting the game somewhere? Or is it ensuring that the hits we do make actually turn into quick, ethical kills?
Wow, yeah. That really puts things in perspective. We spend so much time, so much effort practicing our form, getting raider groups,
And that's important, but
but maybe we need to spend just as much mental energy and maybe budget on the arrow itself, making sure it's up to the task.
the data really points that way. Statistically, Ashby references data suggesting more animals are hit than are actually recovered.
That's a sobering thought.
It is. And the study challenges the idea that just making everyone a better shot is the whole solution. Because if your arrow setup isn't built to penetrate effectively, even on a slightly off-angle hit, or if it encounters bone, well, better accuracy might just mean wounding more animals just in slightly different spots.
Oof. Okay. Let's shift slightly. Blood trails. Huge topic for bow hunters, right? We often use the amount of blood we see to judge how good the hit was. What does the study say about that?
Yeah, it cautions against relying too heavily on just the blood trail volume as your main indicator of, how effective the arrow was or how bad the wound is.
Really? Why?
Because the research showed that the amount and type of blood trail, it's much more dependent on where the entry and exit wounds are located and which specific organs got hit.
Ah, okay.
It's totally possible to get a pretty impressive looking blood trail from a wound that's actually quite superficial, not lethal at all. Think about how much a small cut on your scalp can bleed sometimes.
That's a great analogy. Yeah, lots of surface bleeding doesn't necessarily mean deep critical damage.
Exactly. For a quick, humane kill, what you need is that deep penetration into the vital organs, lungs, heart, liver, causing massive internal bleeding.
Right.
The more vital tissue that broadhead slices through, the faster the animal goes down. And the study suggests the biggest aid to recovering an animal isn't always just a huge, splashy blood trail.
What is it then?
It's the certainty of a lethal hit, which usually means achieving that deep penetration, ensuring the broadhead got into the core vitals. That leads to shorter, more definite recovery trails.
Certainty through penetration. Got it. Okay, so deep penetration is the goal, relying on structural integrity and good flight. Now, the study throws a curveball, I think, for a lot of hunters regarding arrow materials. Specifically, synthetics like carbon and aluminum versus hardwood.
Yeah, this is one of the most maybe controversial or surprising parts of Ashby's findings for many people. There's this really widespread assumption that carbon or aluminum shafts are just inherently stronger, tougher.
It seems intuitive, right? Modern materials.
It does. And the study even mentions that old myth that you just can't shoot wood shafts, especially not from a compound bow because they'll just explode or
Lots,
something.
I've heard that too.
But Ashby himself used hardwood shafts, specifically forge woods, with his own compound bow for years, both hunting and in testing. And his results showed that idea is just, well, wrong.
Okay, so what did the data actually show about durability?
It's pretty stunning, actually. The findings show that specific types of hardwood shafts, and we need to be clear, this isn't soft stuff like Port Orford cedar, it's things like hickory, ash, laminated birch, ipe, purple heart, forge wood.
Okay, dense woods.
Right. Those dense hardwood shafts were 10 times more durable on hard impacts, especially angled bone impacts, than either carbon or aluminum shafts.
10 times.
10 times. And that held true regardless of the bow-type compound recurve longbow.
Wow, that's a massive difference. Does the study give specific numbers?
It does. Looking at the data up to 2006 for static shots into downed animals, so controlled impact tests, the damage rate for those hardwoods was only 3.2 per 100 shots.
Okay, 3.2% basically.
Compare that to carbon at 31.8 per 100
Per-
and aluminum at 33.6 per 100.
Right.
So roughly a third of the synthetic shafts were getting damaged on these impacts.
That's huge.
And remember, that's just damage from the impact itself, not counting anything the animal might do to the arrow after the shot.
And the study connects this back to real-world hunting, right? Something about angled bone hits.
Exactly. Animal bones aren't flat plates. They're angled, curved, complex structures built to withstand force. So even on what looks like a perfect broadside shot, your arrow is very likely going to hit bone at some kind of angle.
Makes sense.
And that's why just testing arrows in, say, foam or gel doesn't tell the whole story. Those materials don't replicate hitting angled hard bone. That's where the structural differences really show up.
And with the synthetic shafts, the study found that about 1 out of every 3 hits involving hard bone or an angled impact resulted in damage. To the shaft, insert adapter, something failed.
Yep, around a third of the time. That's a lot of potentially lethal hits being compromised because the air system couldn't handle the stress.
Yeah.
And maybe the hunter doesn't even realize it happened, or they blame it on hitting a rock later or something. Ashby suggests that this high failure rate is partly why that myth of no arrow can break heavy bone persists.
Yeah, because people are using arrows that aren't really up to the task.
Right. That, combined with maybe not the best broadhead choice for bone, and often using arrows that are too light overall to carry the momentum needed to punch through dense bone, the study makes it clear. A properly set up heavy arrow can and does break or penetrate heavy bone consistently.
Okay. So this naturally leads into the next phase, the quest for a better carbon shaft, right? Especially with extreme FOC setups becoming more popular. What's the connection there?
With extreme front of center, or extreme FOC arrows, where you have a lot more weight up front, like 20%, 25%, even 30% or more of the total arrow weight,
Yeah, seen those.
they offer this amazing potential for increased penetration, because that forward weight bias really helps pull the arrow through. But,
There's always a but.
right, that potential is totally wasted if the shaft itself breaks or fails on impact. You get these massive impact forces with heavy SOC arrows, and standard carbon shafts just weren't always holding up.
So carbon is easier to build an extreme FOC arrow with because you can add weight up front easily?
Generally, yes. Much easier than with wood or aluminum to get those really high percentages.
But their advantage in FOC was being undermined by their lower structural integrity compared to those hardwoods.
Exactly. The study even mentions some attempts like double shaft carbons, sleeving one inside another, which helped durability, but they often ended up too heavy in the back end unless you added a ton of weight up front, which kind of defeated the purpose for optimizing FOC.
Right, messing up the balance. Okay, so this challenge led to the development of internal footing, or IIF?
Correct. Internal footing was this multi-year project specifically aimed at figuring out how to seriously beef up carbon shafts, especially for these demanding extreme FOC setups. The goal was simple: get the penetration benefit of high FOC without the high failure rate of standard carbon.
Okay, so how does it work? What's the basic idea behind internal footing?
The core concept is reinforcing the front end of the shaft from the inside. You create this really strong connection between the insert and a good portion of the inner shaft wall right behind it.
Like an internal sleeve.
Sort of, yeah. This strong coupling helps dissipate those direct head-on compression forces from impact much more effectively. Makes the front end much tougher.
Okay.
And then extending back from that really solid front part, the internal footing is designed to provide sort of graduated support. It helps redistribute the bending or flexional forces you get on angle hits, spreads the stress out instead of letting it focus on one weak spot.
Ah, interesting. So it combats both direct compression and the bending forces from angled hits.
That's the idea, almost like an internal shock absorber and structural brace combined.
Okay, sounds promising. And the 2007 testing in the study update specifically looked at these IF designs. What did they find?
Yeah, they put them through the ringer, and some key things stood out. First, the hardwood shafts continued to be impressive.
Still holding strong.
Yep. 19% of the shafts tested were hardwood. Many shot deliberately into heavy bone at bad angles, scapula, leg bones. Zero damage, none.
Wow, and that just keeps reinforcing that point about hardwood durability. What about those double shaft carbons?
The carbon-on-carbon double shafts, when they used long brass inserts and steel adapters, also did well. No damage on tough angled bone hits.
Okay.
But there was one failure with a double carbon shaft that used aluminum inserts. It actually broke behind the insert, just hitting ribs on a broadside shot. Didn't even penetrate the first rib fully.
The aluminum insert seems like the weak link there.
Seems likely. And interestingly, that shot also resulted in the first bent steel adapter they'd seen in the entire study.
Yeah,
Shows the forces involved.
yeah. Okay, and what about just regular standard carbon shafts in that 2007 testing?
Standard carbons, which made up a good chunk of the shots. Well, they continued to show that high fracture rate, almost 32%.
Still around that 1 in 3 failure rate.
Pretty much. And this was mostly on broadside shots, just hitting ribs. The study noted that almost 87% of those fractures happened right when the arrow hit bone and stopped penetrating. Really highlights how much stress even a rib impact puts on a standard carbon shaft.
Definitely reinforces the need for something stronger if you expect bone contact. So, the moment of truth. How did the internal footing shafts perform?
This is the really exciting part.
Hmm.
20% of the shots use these new IF reinforced carbon shafts, all set up for extreme FOC. And they deliberately targeted tough shots, mostly bad angle impacts on heavy leg bones.
Okay, the hardest tests.
Exactly. And the result, not one single IF shaft was damaged. 0 failures.
Whoa. Okay, that's significant.
Hugely significant. It strongly indicated that the IF design was actually working, providing that major boost in structural integrity they were looking for.
So it seems like they cracked the code, at least in principle. Did the study share any details about how they made the IF work best? I know you said some was proprietary.
Yeah, they didn't give away all the secrets because they were thinking about commercial development, but they did share some key learnings,
Like what?
like needing that really solid, well-supported front section to handle the initial hit. But, crucially, the part of the footing extending further back needed some ability to flex progressively.
Not just a totally rigid rod inside.
Right. If it was too rigid, it didn't redistribute the bending forces properly. They found that gluing the entire IF solid actually made things worse sometimes because it prevented that needed flex. So they had to figure out how to anchor just the right amount of it, allowing some controlled slippage further back. Lots of trial and error there.
Fascinating. Sounds like complex engineering. What about putting them together? Any tips from the study?
They stress clean assembly, cleaning the inside of the shaft, and the inserts really well before gluing. They use JB Weld mostly.
Good old JB Weld.
Yep. And for one version made of hard nylon, they even cut grooves in it and a spiral cavity shape to help the glue get a better mechanical lock. They also floated the idea of maybe threading future IFs to screw into inserts, or even making the insert and footing as one single piece.
Streamlining it makes sense. But there was a big warning about using aluminum components with IF, wasn't
Oh, absolutely. Huge warning. The study basically said, don't bother using aluminum inserts or adapters with an IF shaft, because they found it frequently led to the carbon shaft itself cracking right at the insert, even if you used a steel broadhead adapter. The theory is the softer aluminum just compresses too much under those extreme impacts.
And puts weird stress on the carbon edge.
Exactly. It undermines the whole point of the reinforcement. So brass or steel components were strongly recommended, basically essential for IF setups.
Got it. Brass or steel only for IF. Okay, last big piece. How did these things fly? Aeroflight is still critical, right?
Still critical. And the good news was, yes, you could get perfect flight with IF arrows. Tuning them was pretty similar to tuning other extreme FOC arrows.
But there was a catch, right? Something about spine.
Yes, a really important difference, because the internal footing makes the front part of the shaft much stiffer and effectively shortens the working or flexing part of the shaft.
Changes the dynamics.
Totally. It shifts the center of pressure. The upshot is you need to use a significantly weaker spine-rated shaft than you'd normally expect. Much weaker.
Even with heavy points.
Yep, even with really heavy points for that extreme FOC. The study gave examples using 80-90-pound bows needing shafts splined for much, much lighter weights. And for normal-length arrows with IF, you need a less stiff outer shaft to get the right dynamic spine for clean flight.
Okay, that's a key tuning consideration. You have to go way down in spine stiffness.
You do. But the study points out this is actually kind of a bonus for extreme FOC.
How so?
Because needing a weaker, less stiff shaft means the shaft itself can be lighter, especially towards the back. Less weight in the rear helps you push that FOC percentage even higher.
Ah, so the IF makes it stronger, and the resulting need for a weaker spine helps you optimize FOC even more.
Exactly. It's sort of a win-win. You get more strength and potentially even better penetration from the higher FOC that the weaker spine allows you to achieve more easily. And Ashby's data suggested that penetration kept improving with FOC up past the 30% mark they tested.
Very cool, a synergistic effect. Okay, so the study was wrapping up that section looking forward, right?
Yeah, it mentioned they expected IF systems might become commercially available pretty soon, and that the next update would dive deeper into IF testing results and some new findings on FOC, stuff that would be important for everyone, but maybe especially guys hunting bigger game or shooting lower poundage bows.
Okay, so wrapping up this deep dive on the 2007 update, part two. The big picture is pretty clear, isn't it?
I think so.
Shot placement, still vital, you gotta hit the animal well, but it is absolutely not the only thing that matters. Maybe not even the most important thing in some situations.
Right. The arrow's structural integrity, its ability to hold together on impact, that's number one for ensuring penetration.
And number two is clean, stable arrow flight to deliver that energy effectively.
Yep. And then we saw that surprising data on hardwood shafts being incredibly durable.
10 times more.
And this really promising development of internal footing, potentially revolutionizing carbon arrow performance, especially for deep penetration with extreme FOC setups.
It really challenges a lot of common thinking in the bow hunting world, forces you to look past just the point of impact.
It does. It makes you analyze the whole system.
Hmm.
The arrow, the components, how they interact on impact.
Absolutely. So maybe the final thought for everyone listening is this. Based on what we've just talked through, how might you look at your own arrow setup differently?
Yeah, that's the real question.
Are you putting enough thought into the structural integrity, into making sure that arrow flies perfectly, not just accurately, but stably? How tough are your components?
Are you maybe relying too much on just hitting the perfect spot and not enough on ensuring the arrow can handle things if the hit isn't quite perfect or if it hits bone?
Right. Think about it for your next hunt, your next equipment choices. How can you build an arrow system that gives you the absolute best chance for a quick, clean, ethical kill every single time you release that string? Whether you're after whitetails or something much bigger, it's about making sure the arrow can do its job when it gets there.